All right, so welcome back, everyone. For the next hour and change, I'm going to talk about how we actually designed and built the stations that we installed last year in May and that we've been improving since then. And then we'll have a practical example where we look at some of the data that I've collected and look at what are the practical problems of actually working with this really high frequency data. So, one of the big goals of the research project that I've been doing, and also Bodo is working on, is monitoring alpine rivers. So, we're not just concerned about what's going on in the alpine region, but also how it has impacts further downstream. For some big rivers in particular, you can monitor them from space. So, for example, this is somewhere a little downstream of the River Koshi, where you can get an accurate measurement of the height of the river from space. There are some similar to this little laser that I was showing you and measuring how far my hand was away from it. You can do the same thing from space. However, you don't get measurements very often. And the accuracy is, of course, not as high as if you're looking at it directly from only a couple meters away. So, for example, this is one time series from IceSat data, which gives you a pretty good measurement of the height. You can certainly see the seasonal changes, right? But this is pretty low frequency. You get maybe a measurement every month or so. So you can get a good idea of the sort of broad seasonal pattern, but you don't get a really any idea about these short events. So as a comparison, this is just 2 weeks of data of river surface temperature that I was taking from one of my my sensors, and this is something like 300,000 data points, right? So this is a completely different scale of river monitoring that we're trying to see. And it's still an open research question whether we really need data at this high frequency, if this is really giving us a lot of extra information, or if it's too much. So that's also one of our research goals here, to figure out really at what time scale do you need to measure the river to understand how things are changing. So, yeah, the goal of the first iteration of these river monitoring sensors was to measure river heights, take pictures of the river, and get river temperature. With the goal that these are sort of parameters that you can measure from outside of the river that give you an idea of is there rainfall coming in, is there snow melt. The color of the river can tell you something about how much sediment is in the river. So the first iteration was to see, do these sensors survive also in the monsoon, in the rain? How do we really need to design the power consumption and things like this? And now that we've had these sensors up here for almost a year and they're all working quite well, we're adding the extra iteration to try to put something in the river and see how that goes. One of the things that we talked about a lot with the colleagues in the hydropower sector is that they want to know about sediment flux. So when you have these turbines spinning super fast and there's really hard sand going in there, you can destroy those turbines really fast. So having an idea of how much sediment you have at different times of the year, or having some warning of there's going to be a bunch of sediment coming in the next few hours, that can also help to change how the plants are run. And also to think about how much sediment they should expect to be infilling some of these dams. So throughout all of these different sort of research aims, we wanted to only use open source hardware and off-the-shelf hardware. So we were trying to not go through designing our own chips, but rather just take lots of different parts that were already available and put them together in new ways, with the idea that we could produce a manual for how these things were built if other people wanted to take some of these ideas and install similar stations. So the first thing we wanted to measure was river heights. And so this GPS that I passed around, right? This is just this little antenna and the little GPS chip. The reason we used this was, there's basically two main reasons to use this data, the GPS data. The first is that GPS has a clock. So if you have your data and you're away from the internet and your computer or your Raspberry Pi is turning off very often, it doesn't always remember what time it is, right? If there's no battery and it turns all the way off, it starts thinking it's 1970, right? It goes to this default clock. So the nice thing about GPS is that there's a clock. Every time you get a GPS signal, it tells you what time it thinks it is. That's part of how it works, how far away in time different satellites are. So that's one useful thing, to keep all of our sensors on the same time syncing. And the second really nice feature is that GPS data can be used to measure flat surfaces. You can measure the change of a surface. This basically works from whenever you have a GPS satellite, it is always sending a signal down to the Earth. Your phone is receiving it, my GPS tip is receiving it. We're just always getting hit with GPS signals from several different satellites at the same time. And what a GPS antenna can do, if you set it up to measure this, is it gets both the signal directly from the satellites, and it can get a signal that goes and hits a surface and is reflected to the same GPS receiver. This basically can tell you how high you are above that surface. And if you think of something like a lake or a river or a reservoir that's going up and down, as this angle changes, right? If you're going really low, you have this angle. If you're going a little bit higher, you have this angle. That can tell you directly how high this surface is. So this is a really easy way to measure these surface heights. All you need is a good view of the sky. So if you're in a really narrow valley, it doesn't work as well because you don't see very many of these GPS satellites. But if you're in a rather open setting, like by a big lake or something, then this works super, super well. And we're talking about accuracy of 1 or 2 centimeters. So it's a pretty high accuracy thing. If you have a sort of a fancier GPS antenna, like the one Bodo is going to talk about later, you can get much more accurate and much higher time frequency. So down to 15-minute time resolution. With these cheaper sensors, you can get maybe 1 or 2 hours of time resolution, depending on how much of a view of the sky you have. The other way that we measured river heights is with these LiDARs. So this thing I showed you where I can measure how far my hand was and how far the wall was, this works just the same for measuring how far away you are from the water. It works best, of course, when you can look directly down at the water and you don't have to worry about doing some trigonometry and figuring out what angle you are. And it also, of course, works best if you have smooth water. If you have water that's really rough, if you're by a bunch of rocks or rapids, then you're going to get really a lot of changes in the river height really fast. So if you have a piece of the river that's a little bit flatter, or if you have a storage dam, or if you're behind like the big dam and you want to know what your water level is, you just point one of these down. When we looked at some of these hydropower plants, they were doing something similar with painted numbers on a wall and then a webcam. And so they were monitoring how high the water surface was based on just visually looking at the heights there. This could also be accomplished with something like this. Of course, before you switch your system, you'd have to spend some time making sure that everything was well calibrated. But this could also give you a more direct time series rather than just keeping an eye on how high the levels were, for example. So this is something that we use, and I guess it's a little hard to see here, it's over in the corner. I also put an air temperature sensor in there, just so we have an idea of ambient air temperatures as well. In the second iteration of this, I compressed it into this smaller box. So this is what the first iteration looked like that we put up last year. And this is the new version, which also has a camera in it. So we are, whatever we're looking at, we're also getting an image of exactly the same line where we're getting distances from. So it makes it a little easier to compare these two measurements. So for this image capture, you can use any sort of USB webcam. There's a lot of different possibilities here. Since we're using the Raspberry Pi as our data manager, data logger, we decided to use the Raspberry Pi camera, which is super minimal, right? It's just this tiny little chip with this camera cord coming out of it. But it's a pretty good camera. It's 12 megapixels, I think. And you have a lot of control over what the quality of the image you capture is. So, for example, when we are capturing a lot of these things, you don't want to capture like an HD video all the time, because you're never going to be able to send that much data all the time. You're going to fill up your hard drive, and just it's going to be problematic to deal with that much data. So you have a lot of control over what kind of resolution of data you want to capture. And I'm going to show you guys a few pictures that are from one of our stations here. The other one that I was passing around here, this little loose sky here, is measuring river temperature. So river temperature is quite important for monitoring basically dissolved oxygen, nutrient content, and correlates with a lot of different water quality indices. And it can also be used for, in our hope, for one of the plans is to use it to track when the source of the water changes. So if you have a big snowmelt event or a big rainstorm, the river temperature will likely change. And that, how fast that change happens and how long the river temperature is different for, those are two things that we're quite interested in seeing. How quickly does that piece of water that came from that rainstorm move through and you're back to the average normal water temperature. So we're measuring it with this thermal camera, and we also have an infrared laser. So I don't have one of these here because they're all already installed out there in the world. But it's this basically a tiny little laser, and it's the same thing if you go to the doctor and they take your temperature with one of these little infrared things where you don't have to actually put something in your mouth. Or during COVID when they had these little webcams when you walk through the airport to check if you have a fever. It's the same exact principle, and probably actually the same exact chip that they're putting in those thermometers. I'm just taking it out and interfacing it with one of my Arduinos. So that allows me to get basically a temperature at one particular spot rather than a whole grid. And this is certainly easier to work with and less error prone than this one that's trying to capture a whole grid, which is why we tried both. All right, so I guess one of these is here. We've installed pretty much all our sensors in these weatherproof boxes. The GPS sensors, or the GPS antennas, they're already pretty waterproof. So we just put them in a little box like this that allows us to mount them on a pole. So for example, this is one example which is off maybe about 8 meters above the water. And we mounted it on one of these barricades that keeps the wall from running out into the river. And just mounted these things on a pole. The exact location that we end up putting these things in is determined to a large degree by where we have access and power and a location that is safe. So you don't want to just put this on the side of the road and hope it's going to still be there in 6 months. You want to put it somewhere that you know that somebody's keeping an eye on it, or it's behind a fence, something like that. But beyond that, if you have a decent location, then you can put this sort of anywhere you want. we wanted to have access to our data as it was coming, so we could actually see if there were problems and see what the data looked like. So we put basically these little Wi-Fi routers with all of our stations, so that we could have access to them, and the data could be transmitted basically every hour. So as Bodo passed this around before, and we talked about before, we use Raspberry Pi to gather all of the data. So if I have, a thermal sensor and a GPS and a camera and a LiDAR, that's 5 or 6 different things that I want to be able to. I don't want to have to send 50 different files, right? So if I have this Raspberry Pi, I can collect all of the data from 1 hour, put it in one little file, and just send that. So it makes it a lot easier to handle all the different data. We used Python, so I showed you before when I did this demonstration with my hand in front of the thermal camera. We used Python for capturing all the data on the Raspberry Pi, and then we used some basic Linux commands, so some of this command line tools to compress the data and send it back to us. So I receive data. My Dropbox is always reminding me that I have new data every hour. So that works pretty smoothly. So where did we actually do this? Here's Kathmandu, and here's where we were working. So we went into Trishuli, and we have some stations here at a powerhouse down there, and this weir a little further upstream, another power generation station up at 3A, Chilime, and then up at a guest house, and finally at Upper Sendon, which is a newer hydropower project. So we put in several different sensors. Not every station has exactly the same setup, so we could try out a few different things. And the idea was that we could sort of see how different signals came downstream, right? Particularly if we have snow melts coming down here, and down here we mostly have direct rainfall. We wanted to see what the difference is in how often the river changed, how did the river temperature change throughout the year, how often does the height change, how rapidly does the height change, things like this. So we wanted to have a good distribution up and down some watersheds here. Here's another one of our setups at the Chilime plant, where we put it sort of, this is a pretty rough looking river here, right? So trying to put something down here when the water is going to potentially come up 2 or 3 meters, it's just not gonna survive. So ideally having something out over the water where we could look would be great, but that's not always possible, right? So in this case, we have a pretty good view for our GPS, where we're getting a timing signal and some reflections off of the water here. And then we have our LiDAR, we have a camera, and then we have the thermal camera. So this is what some of the data looks like. This is, for example, what our GPS water heights look like. This is one of the downstream stations where we have a nice big flat area. And you can see we have basically almost 3.5 or 4 meters of height difference that we're tracking. And we have basically these squares here are the daily averages, and then the blue ones are the not so tightly quality controlled data. So we get a lot of nice data around here, and then of course there's always some noise when you're working with this really high frequency data. The same thing is also happening for our LiDAR data. The ones that we have a really nice straight down view, we have less problems with, but even then we still have some times where potentially something is flying under there, or there's a plant floating in the river. There's all sorts of things that can impact this. Air temperature and river temperature are probably the easiest things that we get to measure, because you don't really have to worry about something getting in the way between your sensor and the river. The main thing that makes this data a little bit trickier is when you have a lot of sunlight, right? So if you have a lot of direct sunlight coming onto your sensor, then you get these 40-degree temperatures. I don't think it was so often 40 degrees up there in parts of this. But if you're sitting in direct sun in this box getting hit at noon, then you're going to get pretty warm down by these sensors. So this is why you have some of these lower days here. So these would be cloudier days where the peak temperature is quite a lot lower. So it's not only a little cooler, but you don't have this direct sunlight thing in there. So the main takeaway from that is that the GNSS, the GPS data, is really, really nice in big open areas, but it's a little bit trickier in steep valleys. And the LiDAR works really well if you have a good and close to vertical view of the water, and it's a little bit trickier if you're at a lower angle. Temperature data we're collecting basically at a 1 minute interval, both from the sort of the ambient temperature and also the river surface temperature. And this works really well. We have a really nice view of how much the river temperature fluctuates throughout the day and through the year. Some of these temperature changes are also, of course, sunlight, right? If you're measuring how much thermal energy is on the surface of your water and you have sunlight reflecting off of it, you also get a little bit of contamination there. But in general, we see quite nice data, and it makes sense that the higher elevation ones are colder, and the lower down you go, the water gets significantly warmer. On the same day, we're talking about a 7 or 8 degree difference if you're way up in the mountains and down in the valley. So that works really well. The thermal camera is also quite interesting. So this is from the side view at Chirime, and you can basically see where the edge of the water is, and then you get the warmer land. And the water temperature is pretty consistent, but this isn't the case for all of the different stations. Some have warm and cold spots that we see also in especially in some of these reservoirs where you have the river water coming straight in, and then you have parts where it sort of sits for a little while before it goes back out, and you have differences in temperature between the higher and lower flow parts of these reservoirs. So this is nice. It's cool to be able to see it, but again, these are so much harder to work with, the thermal cameras, than these spot thermal data. So we're mostly moving to just using the single infrared sensors now. Just as like a comparison of what this looks like versus satellite data, this is the whole Landsat temperature record for all of our sensors. For the Landsat satellite, you can get the temperature of a surface, and if I just pick out the water area right by our sensors, I can get basically all our different temperature data from 2014 to 2024. However, it's really, really sparse. If you really work at it, you can get an idea of the seasonal temperature fluctuations. But if you start looking at, for example, just a couple months of data, it really is not great. So this is the same amount of data as this, basically. So we're talking about a completely different kind of analysis that you can do. What we can do with this is use this to calibrate these values and make sure that our sensors that we installed there match up with the satellite, or rather that the satellite matches up with our real data. This is always interesting to look at. So this is the side view down looking at Chirime, and you can see how high the water goes up. So this is the period from, let's run this again, from May until August. So right as the monsoon comes in, it really starts going up, up, up a lot. So this is something that we could use to track the change in the bank height. And also, you get an idea of that the color is very different too. I guess it's a little harder to see on the projector, but this is a lot clearer than this. So something that we hope to do now to be able to introduce sediment sensors, if we can match that up with the image color, it would be nice to be able to estimate how much sediment is in the water without having to stick something in the water that could get destroyed. So that's another new goal here. We also collected some video data. So this is from also that same location. This is just from a couple weeks ago. And the idea here is that you can look at how some of these bubbles basically are moving down and get an idea of how fast the water is going. So flow velocity is also something that is quite interesting to see how that changes through time. So we have been collecting this data and we haven't had time to fully analyze it yet, but it looks promising for getting some at least basic idea about how the speed of the river changes throughout the months. Yeah, so those are the main things that we want to do with this image data. Look at how the bank width is changing, look at the color of the water, and also do some tracking to see if we can get some flow velocity. So then coming back to sediment flux, we took this picture last time we were up there of one of these turbines that they had taken out for repair. And these things are, thick steel turbines, and they're just getting completely shredded. It's like thin as paper. You can see all this scarring here. That's from all this sediment constantly running through these turbines. So this is a pretty easy way to think about it, but you also can think about the reservoir infilling, or if you're pumping water for irrigation and you start filling up all your irrigation pipes. Also for water quality, if you're putting this into the water systems of towns, right? The more sediment you have in there, the more you're going to destroy your pipes, right? So having idea of when and where sediment is entering the river and how much sediment is entering the river could be really useful for a lot of different applications. So our first generation of the sediment flux was this. It's based on a similar thing where we have an Arduino and then a couple of sensors and a thermometer here coming out the end. And it's based on the principle that when you have clear water, if you put out radiation into that water, basically if you shoot a laser into the water and it's clear, all that energy just keeps going. It doesn't bounce off of anything. If you have a lot of dirt or rocks or something floating around in the water, then you shoot some laser, a lot of that energy is going to get reflected back. So this sensor that we're using, this is the main one here, it's actually built for like opening doors automatically. So, if you go close to a door and it sees that your hand is there and opens, it's a small infrared sensor. So this is something that is commercially made for a completely different purpose, but also works to give us basically the strength of the reflections from any dirt that's in the water. The second version of this, I have this here. This is the thing that is always fun to go through airport security with, because they look at you a little funny with this device with all these wires coming out of it. I can pass this around as well. So this version then has the data logging is in here, and then we have a couple different sensors. So these sensors will measure the reflected radiation, and this other sensor that's a different shape will measure the depth and the temperature of the water. So we get a few parameters. And we have a few of these that we're going to hopefully install in the next weeks, and then we're going to see how they survive through the monsoon. But this could be quite interesting data as well. Just to show that we're not just making this up, we also did some lab tests just to see how sediment concentrations. So sediment concentrations here on the X, and then the reflected values here on the Y. We get a really nice linear relationship when we start doing when we basically add more and more sediment. The backscatter, the amount of radiation that we get back from the sensors, goes up, and it's a pretty nice linear relationship until you get up to these really high concentrations where it starts to get a little bit more difficult. This is where we installed our first prototype down in India in the Ganges. So at a huge river, we found a nice little site that they used, I guess, they took showers down there. They had this little blocked off area of the water, so we managed to put it in on this fence, and we're getting some nice data back that we get a pretty good view of the water temperature. Of course, there's some days where the river goes down too much and now we're exposed to sunlight, so the temperature gets a little funny. And our sediment data is also changing throughout the day, or not just throughout the day, but more on a multi-day cycle, right? We don't have this same kind of short up and down like we have with temperature, but it's changing at a much different scale. So that tells us that, yeah, the data could use a little bit of cleaning here, but we're getting something useful about how the content of the water is changing. Yeah, so that's what we've been doing in terms of designing and building these sensors. Questions? Or comments? Other things that might be interesting to measure from a river?